Okay, just a quick summary where we left off a week ago today. We were looking at external flow, and we started off with the simplest geometry in external flow, which is a flat plate. And for that situation, I'll draw the picture over here. It's laminar from the leading edge, x equals 0. It's laminar if the Reynolds number is less than or equal to 500,000. So if that's satisfied, then if this plate at the end at x equal L, the Reynolds number is 500,000 or less, we have all laminar flow. If we have all laminar flow, here are the equations we looked at last time. First of all, the boundary layer thickness anywhere. Now, don't forget what that is. The boundary layer thickness is this value right here. It's the height of the boundary layer. We call it the thickness of the boundary layer at a particular x value. Okay, so there it is right there. We then talked about finding the shear stress at the wall. The shear stress at the wall is the value at y equals 0. And again, y is measured vertically up from the plate surface. So at y equals 0, that's the shear stress. Tau w, the w means at the wall. Tau at the wall, here's the value. We use the definition of the wall shear stress in terms of a dimensionless term here, C sub f. If you recall last Monday, C sub f was called the skin friction coefficient. So if you work backwards, these two guys are equal. Tau w equal the same. Solve for C sub f by equating these two values right here, and you get this value right here, okay? Double check your notes and make sure there's not a u in front of that square root. I think somebody last time after the lecture said there was a u out here. It shouldn't be. The u is on the end, u to the 3/2 power. So if there's a u after that 3, 3, 2, get rid of it in your notes. Okay, back over here. Okay, now we're interested in several things on flow over a flat plate and laminar flow. We're interested in finding the boundary layer thickness. Okay, there it is. We're interested in finding the shear stress at the plate surface as a function of x. There it is. We're interested in finding the drag force on the plate. Okay, the drag force. The drag force, we integrate the skin friction times the differential area along the plate surface, dA, because stress times an area is a force. So integrate stress times dA, that gives us differential force. Integrate from x equals 0, for instance, to the end of the plate at x equal L. Okay, there's the equation when you do that. We put that down last time. Again, double check, make sure it's u to the 3/2. There's no u in front of the radical sign. And we also define something called the drag coefficient, capital C, skin friction coefficient, lowercase c, F means friction, D means drag force. Our textbook uses capital D for the drag force. I prefer to use F sub D. I mean, most people think D is diameter, so I don't want to confuse anything, so I'm going to use F sub D as a drag force. The drag coefficient C sub D times the area of the plate. The plate is L meters long, B meters in width. That means out of the blackboard. Rho u squared divided by 2. Since these two guys are equal, you solve out for C sub D, the drag coefficient. The drag coefficient then is right here. So that's the important equations that come from laminar theory, and they're derived analytically, okay? Our next step is to go to turbulent flow. Okay, so now we have turbulent flow. We're going to assume to start with that there's turbulent flow all along the plate, okay? The turbulent flow starts at the leading edge at 0. It's turbulent from that point because somebody caused it to be turbulent. I think we may have mentioned that you can artificially roughen the surface here with sand particles or sandpaper or a very thin piano wire at this point, x equals 0. When you do that, the boundary layer trips immediately to turbulent flow. So in the world of the textbook, it might say, assume turbulent flow from the leading edge. Okay, that's this picture right here. Assume turbulent flow from the leading edge. If that's the case, now the mathematical analysis is very different from laminar. We don't do it totally mathematically like we did for laminar. There's no exact solution. Numerical methods, computer solutions are used. We use a 1/7 power law velocity profile with the integral approach, and that particular velocity profile would look something like this in equation form. That's valid for Reynolds number less than or equal to 10 to the 5th. 10 to the 7th, I think it is. Let's double check and see what he puts down here, if he did. Yeah, 10 to the 7th, I think it is. So if you do that, and it's a couple pages in the textbook, they walk you through it. We're not going to walk through it, okay? We're going to use the results of that. But if you assume a power law velocity profile in the boundary layer, turbulent boundary layer, and you go through the integral approach, what you end up with is this. Here's delta as a function of x for a laminar flow. Here's delta as a function of x for turbulent flow. And tau wall and skin friction coefficient. If you do the same thing we did over there, back it out of this equation, skin friction coefficient just so you know, this is equation 744 in the white textbook. This is equation 743. If it's laminar flow, here they are. Tau wall, laminar flow, C sub F, laminar flow, turbulent flow, tau sub wall, C sub F here. If you want to find the drag force over this plate in turbulent flow, That's equal to our C sub D times the area rho u squared over 2, where the drag coefficient, C sub D, and that goes with this down here, the drag equation for laminar flow, where C sub D is this number. Now C sub D is this number for turbulent flow. That was now considered turbulent flow. Now consider mixed flow. As the name implies, mixed flow is part laminar and part turbulent boundary layer. Flow starts out laminar. It gets to a location called X sub C. The C stands for critical. So X sub C is a location where the boundary layer transits from laminar to turbulent. So this is laminar. This is turbulent. We're going to assume that it transitions to turbulent at 5 times 10 to the 5th. Okay, so the Reynolds number then, 5 times 10 to the 5th equal U X sub C over nu. So solve that for X sub C. X sub C is equal to 5 times 10 to the 5th times nu over U. For this case then, F sub D, drag coefficient, okay, times our area, B times L. L's the plate length, B's the width, times rho u squared divided by 2, where C sub D now is this. Because there's part laminar, part turbulent, so you have to kind of integrate this in pieces. You integrate the laminar part, the turbulent part. That's why there's 2 terms in here with a minus sign. The textbook goes through all those details. Takes about half a page to a page. So we're going to use it, so that's what we're doing here. So there's 3 cases to worry about. I know people this morning that had my heat transfer class at 7 or 8 a.m. and 9:15. This looks very similar to that lecture. Of course it does, because we were doing heat transfer with thermal boundary layers. So when you get into this class, at this time of day, you got to kind of shift gears. Okay, now we're looking at velocity boundary layers only. Okay, but it's very similar, very similar. 3 possible cases. Case 1, end of the plate, the Reynolds number is less than 5 times 10 to the 5th. The flow along the plate is all laminar. Here are the equations. If somehow the boundary layer has been tripped artificially, like if the flow is over this table here again, and the flow hits this table, it's a sharp edge, assume, sharp edge. The flow fans over there. Boundary layer builds up. Okay. It might be laminar, and after a certain distance, x sub c, it transits to turbulent. But if I put a fine piano wire and glue it on here, or if I put a glue stick down here and spread sand particles on that glue strip, now as soon as that velocity hits that particular x equals 0 location with either sand on there or a piano wire, that's called surface roughness. And the boundary layer trips immediately to turbulent. There is no laminar part. Okay, that's this guy. No laminar part. If the textbook says in a problem, assume the flow has been artificially tripped at x equals 0 to turbulent flow, this is your picture. If the textbook problem says nothing at all about that, then this one or this one is your picture. Okay. Check the Reynolds number at the end. If it's less than 5 times 10 to the 5th, use these. If it's greater than 5 times 10 to the 5th, use this. If you want to find the shear stress in this part, use that. Laminar part. Okay. So there are the equations on the board for the 3 possibilities. All laminar flow, all turbulent flow, or mixed flow. Okay, there's also a graph that I'll put on the board here. Okay, I really don't need that, so I'll put it there, I think. This is figure 7.6 from the textbook. Now, you don't need to copy it down. I made copies for you, so I'll give you these copies. I'll put on the board exactly what's on this page, though. Okay, so here's what the figure is. On the x-axis, the Reynolds number based on L. It's logarithmic 10 to the 5th, 10 to the 6th, 10 to the 7th, and so on. The y-axis, it's linear. That's C sub D. 5 times 10 to the 5th is right here. Now, you know that the trick question you ask somebody. That's a log axis. Where do you think 5 times 10 to the 5th is? And the guy says, well, I think it should be right in the middle. No, you're not thinking logarithmically. Your mind's not thinking logarithmically. Where is that? Well, it's 70% of the way over of the total distance. If that's 10 inches, that's 7 inches over. So, no. There's where 5 times 10 to the 5th is here. So some people have difficulty reading a log scale because they think linearly, like rectangular log scale. Okay. So anyway, there's 5 times 10 to the 5th. Right there. Okay, let's make a dash line there. Now, you can see here, Laminar, he says, equation 727. right there. Starts up here at around 0.4, goes down here to 5 times 10 to the 5th. Stop. Okay. He marks it a laminar equation. I'll put it here, but in the picture in the textbook, he says that's laminar flow, and that's equation 727. At that time, it's going to transit to turbulent flow. By the way, let me just mention so you don't think this is true. This X sub C, does the flow immediately transist from laminar to turbulent at that particular location? And the answer is no, it doesn't. There's a gray region here. We don't know where it might transist in that region. It takes a little distance for it to transist from laminar to turbulent. But for the sake of the textbook world and our homework world and the exam world, we use a magic number. We assume the flow transits exactly at the point 5 times 10 to the 5th. In reality, that's not true. There's a region where it transits from laminar to turbulent. Okay, back over here. All right, magic number 5 times 10 to the 5th. Other people use different numbers. If the free stream velocity has some turbulence in it, a little bit of turbulence, it's going to transist at a lower one. If you take really, really, really good care to make this start out to where it's laminar and the incoming flow is perfectly parallel velocity vectors, and let's say the air has been sitting in a tank for days, there's no motion in the tank of the molecules, they're perfectly still, then maybe it won't transist until 7 times 10 to the 5th. So it depends on many factors, one being free stream turbulence. But again, in our case, it's going to be 5 times 10 to the 5th. Okay. You can see at that point, now let's go to the turbulent one. Turbulent smooth starts out here at about 6 and goes down below 2. So here's turbulent smooth. It keeps going down like this. So this line is turbulent smooth. That's equation right here. He tells us it's equation 745. This is equation turbulent. That's not turbulent. Here, okay, equation 745. So plot that guy over here. Now, if it transits from laminar to turbulent at what magic number? 5 times 10 to the 5th. That's right here. You can see what happens. This curve goes up here and goes like that. And then he says, this is equation 749. And here it is down here. Equation 749. So I erased most of it, but no, I didn't. It's over here. Okay. If we know the Reynolds number is less than 5 times 10 to the 5th, on this graph, what line do we follow? That line right there until you get down to where my finger is. That line right there. Okay. If the flow is all turbulent from the leading edge, it's been artificially tripped to turbulent flow leading edge, which line do you follow? This line, all turbulent, all the way down to there. Okay, let's go to where it's mixed flow. Starts out laminar, goes to turbulent. Now you follow this line on your road map. You go down this highway, stop, then you go on this shortcut, stop, then you go down turbulent flow. You don't have that guy right there. Okay, that's mixed flow. You want to see sub d mixed flow? There it is for you. Read the graph. Not very accurately, of course, but you can read the graph. Or you can use the equations. You know, the choice is yours. Oh, by the way, there's other curves, but we're not going to worry about them. There's curves that go out like this. These are for all different values of roughness. L over E. I didn't mention it before, but all these equations are for smooth plates. Smooth plates. If they're rough plates, there's equations in the textbook. We're not going to worry about rough plates right now. Or you can go on these lines right here for the relative roughness. Does it matter in laminar flow? No, doesn't matter. We engineers love graphs like that. Oh, you can use the equations. Of course you have to if you're doing a code, a computer code. You've got to use the equations. But the graphs, people are always interested in graphs. They think, what's going on there? What's causing that to do that like that? And they think the same. They think the same. Okay. You can guess what I'm going to draw here. Dimensionless, dimensionless, dimensionless. Okay, here we go. One more time. ME311. Dimensionless, dimensionless, dimensionless. Oh yeah, there it is. Here we go. One more time. Is there an equation for laminar flow? Oh yes, there is. Laminar flow, laminar flow. Is there an equation for smooth pipe? Oh yes, there is. Smooth pipe. Yep, there it is. Is there an equation for relative roughness? Oh yes, there it is. Are they similar? My gosh, are they similar? Geez. See, we engineers think like that a lot. And if that helps you see things in the real world, engineering world, fine. That's the whole point of the graphical presentation, because they're beautiful. This was named after somebody, Moody chart. This has no name. This is Mr. No Name, okay, unfortunately. But what do? This is for flow over a flat plate. This is for flow inside of a tube. And I'll tell you something. You know, you can have HF. Oh my gosh, we engineers think alike. Look over here. Where is he? Okay. Reynolds number, okay. Up there he is. Rho V squared divided by 2. Guess what? Flow in a pipe, rho V squared divided by 2. Guess what? Geometry. Guess what? Geometry. Guess what? Dimensionless friction factor. Where'd that come from? Solving the partial differential equations? Oh, no, 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 no. We invented that. So you use this graph and plug it in here. We invented that. Drag coefficient. Boy, are they similar? You better believe they're similar. Oh, yeah. That's the beauty of the graphical part. You say, well, why do you worry about the... Just use the equations. I know you can. But you don't get a full understanding of the whole picture until you look at those graphs. I'll tell you something else. This is a log-log graph. This is a straight line. When I plot this guy, okay, on a log-log graph, this is called a power law, if he's constant. Power law. If you plot this on a log-log graph, you probably get straight line here too, in the laminar region, like a straight line here. What's this guy here? Right there. What's the Reynolds number power? -1. What's the Reynolds number power? Right there, -1/7. So yeah, they're very similar. So, you know, this is on your data package for your exam. So it's hard to read though, so I would recommend you use the equations. But if you want to see where you're going and where you're at, look at this thing. You can say, am I on this curve for all turbulent? Am I on this curve for all laminar? Or am I on this one, and this one for mixed flow? Like that. Okay, so let's do an example. I might want to keep these, so let's see that go. I'll start over here. So we take an example here, and the one we're going to do is air. So example, air. Okay, so here's plate. 20 degrees C. So we'll take U 2.5 meters per second. Did I call that B? I think I did. Yeah, B. B is the width, 3 meters. The plate length is 0.5 meter. Okay, got it. Free stream velocity, 20 degrees C air, got it. Okay. Properties of air at 20 degrees C. Table A2, back of the book. Density, 1.2. Kinematic viscosity, 1.5 times 10 to the 5th. Minus 5, that is. Kilograms cubic meter, meter square per second. I think that's all we need. Okay. First thing, Reynolds number at L. If I do that, I get 8.33 times 10 to the 4th, which is less than 5 times 10 to the 5th. So it's all laminar. Got it. I'm just going to find a lot of stuff about this, so I'm just going to tell you what I find then. Let's find the boundary layer thickness at the end of the plate. At X equal L is 1/2, 0.5. Okay, it's all laminar. Go over there. Delta 5x over square root Reynolds number at X. I've got X, I've got Reynolds number, put them in there, 0.0087. Almost 9 millimeters, a little less than 1 centimeter, 1 centimeter. The plate length is 1/2 meter. The plate length is 50 centimeters. Delta at the end of the plate is 1 centimeter, a little less, 1/2 inch. So it's very, very thin with air blowing over the plate at that velocity. Okay, very thin. The boundary layer is usually very, very thin. Okay, let's go ahead and get C sub F. So, the skin friction coefficient, C sub F. There it is, 0.664 square root Reynolds number. End of the plate, X equal L. Put L there. Put L there. We're at X equal L. You can put X or L, doesn't matter, but we'll just try and, the actual value of X is the plate length L. Put that Reynolds number in here, it's easy. You get 0.00514. Dimensionless skin friction coefficient. So the wall shear stress equals C sub F times rho U squared over 2. So we put C sub F in there, 0.00514. The density, 1.2. velocity 2.5 squared divided by 2. The wall shear stress at the end of the plate. Okay, there it is. Okay, let's go ahead and get C sub D. It's laminar over the whole plate. There it is, 1.328. Over Reynolds number L to the 1/2. Okay, C sub D, yep. We know the Reynolds number, 8.33 times 10 to the 4th. Drag coefficient comes out to be 0.00460. Drag force equal the drag coefficient times the area times rho u squared divided by 2. The area of the plate, the width was 3, the length is 1/2, 3 times 1/2. Density 1.2, u squared 2.5 divided by 2. It's really small for the laminar flow. You don't expect, and this is really low velocity. So that is 0.026 newtons. Just so you can see, that's 5.6 miles per hour, so it's really, really slow velocity. 5.6 miles an hour. That's why the drag force on it's really low. And it's laminar flow, which makes it even lower. Big drag force, turbulent flow, low drag force, laminar flow. All right, part B. This is part A. Part B. Assume boundary layer is tripped to turbulent. At x equals 0, at the leading edge. At the leading edge. The problem says it's been artificially tripped to 0. Okay, there's the equation right there. These are the turbulent flow equations across the whole boundary layer, turbulent flow. Reynolds number, it's the same. Okay, everything's the same, so put that guy in there and you get 0.01585 meters. You can find tau wall anywhere. Give me an x, I'll find you a tau wall. There's the two equations, not a big deal. Give me an x, I'll plug it in there and I'll find tau wall. If I want to, I'll find the skin friction coefficient. But I'm gonna, most of the time we're interested in the drag force on the object, on the plate. So I'm going down the drag force now. Find the drag force on the plate if the flow is turbulent. First of all, get C sub D. C sub D, 0.031 divided by Reynolds number, 8.33 times 10 to the 4th. Okay, put him in there, get C sub D 0.00614. Then get the drag force. Okay, 0.00614 times the area of the plate, the top surface of the plate, 1/2 by 3. Times the density, 1.2. Times U, 2.5 squared, divided by 2. The drag force on the plate, 0.035 newtons. Okay. Drag force laminar, 0.026. Drag force turbulent, oh, it's bigger, of course, 0.035. That's about a 33% increase over laminar. So yeah, the turbulent flow over the flat plate gives a bigger drag force. Okay. Change the problem now. Go back here. You say, keep that at 1/2. No, I'm sorry, change it to 5. Make it longer. Okay, 5 meters. That flow rate's way too low. I want that to be 56 miles an hour. Now the air flow's 56 miles an hour. The plate's 5 meters long. Okay. L went up by a factor of 10. Velocity went up by a factor of 10. They both went up by a factor of 10. Bigger by a factor of 10, bigger by a factor of 10, stays the same. Uh-oh. Nope. Now the Reynolds number at the end of the plate is definitely greater than 5 times 10 to the 5th. So now I say, so it's mixed flow. Okay, now my picture looks like that. Okay. I'm going to find the drag force on this picture now, the drag force. By the way, if I want to find where it transitions, I'll do that first. Find x sub c. So we had it from before 5 times 10 to the 5th equal the velocity 25 times x sub c, the critical x distance, divided by the kinematic viscosity. So x sub c is equal to 0.30 meters. Go back over here. What's L now? L is 5. Where is x sub c? 0.3. Okay. 1, 2, 3, 4, 5. Close. There's 1. Where's 0.3? Right here. Okay, draw a new picture. Ooh, there's just this little piece right here, laminar, then right here, it goes to turbulent. There's a new picture. Okay, so back over here. Got it? Now I want to find C sub D, the drag coefficient C sub D. Okay, mixed flow, C sub D, right there. There's right there, 0.031. divided by Reynolds number to the 1/7 minus the 1440 divided by the Reynolds number. Put the numbers in, the Reynolds numbers right up here, 8.33 times 10 to the 6th. Put that in there. This guy is 0.0046. Drag force then is C sub D times the area of the plate. The width is 3 times 5, times rho, V squared, divided by 2. So the drag force in this case, for the mixed flow situation, is 16.9 newtons. Okay, so we've got that. Let's see, this was trip to turbulent at x equals 0. Okay. And that value, Okay, we don't need this anymore. It's the 10% rule. If x sub c is less than or equal to 10% of L, assume boundary layer is all turbulent. Because the contribution of the laminar part is going to be negligible. So you might as well assume it's all turbulent. Look over here. If I assume it's all turbulent, I'll bet my answer can be pretty close to the real situation, mixed flow, because that little piece right there is the only laminar part of the whole boundary layer. So in our case over here, x sub c was 0.3 meters. Uh, 10% of L was 5 meters. 10%, 0.5. So x sub c, 0.30. Less than or equal to, let's find out, 0.50. The answer is yes. You can treat that as if it were all turbulent. So that's the rule we'll follow for the class. If x sub c is less than or equal to 10% of the length of the plate for mixed flow, assume that it's all turbulent. Okay, if we assume it's all turbulent, then we get C sub D, if it's all turbulent, over Reynolds number, L to the 1/7 power, C sub D, 0.0614. And we get the drag force, C sub D times the area, rho u squared over 2. Zero point 0.035. Let's see, where is our mixed flow, the drag force? Oops, that's the wrong one, excuse me. Here it is. C sub D is, let me get this right here now. That was turbulent. C sub D is 0.00312. drag force, 17.61 newtons. If we do it the right way and assume it's mixed flow, we get the drag force 16.7. Because of the 10% rule, if we assume it's all turbulent, we get 17.61, off by 4%. Is that okay? Yeah, it's okay. I mean, 4% is not that far off. So you can use that rule. So that's how you use a 10% rule, okay? Okay, let's erase this now. .0046. Reynolds number, 8.3 times 10 to the 6th. 8.3 times 10 to the 6th. 8.3 times 10 to the 6th. That's our Reynolds number. Go up here. Go across here, if I had drawn right, which I don't. Okay, you can look at your picture here. Take 8.33 times 10 to the 6th. There it is. And we go up there, and we're, okay, we're at the mixed flow. Yeah, we're close. We're higher than that. But yeah, no, that's right. We are down there. Let me just make sure that's right, that mixed flow one, C sub D. C sub D, okay, I thought so. The answer is correct down there, but I was looking at the turbulent flow. 0.0030, that's what it is. So go up here, go across here. What do I read? Oh, I can read close to 0.003. So the point is, you can do the equation, you get 0.003. You can go to the graph at the right Reynolds number, you can get close to 0.003. It might be 0.0031, I can't tell, or 0.0029, I can't tell, but I'm really close with my eyes reading the graph. You want to go to all turbulent? Okay, let's try that. All turbulent. The Reynolds number, it's the same. Now, I don't have it drawn. I'll show you how it's really drawn. That's how it's really drawn, if you check your graph. Okay. Where's all turbulent? This one. Where's the mixed flow? This one. Where's the 0.30 mixed flow? Okay. Where's the all turbulent one? That big black dot. I read it 0031 with my eyes. What's the equation one? Oh, am I good? I'm off by 6.6 out of 100. That's really good. So what I'm saying is, don't downplay the graph. Think, oh, the graph's not accurate. Oh, yes, it is. It's as accurate as you take the time to read it. Just like the Moody chart. Say, oh, I use the equations all the time. That's okay. But I guarantee you, I'll be really close to you with the equations if I read the Moody chart with my eyes. Because I know how to read those graphs, okay? That's the whole point. So whether you want to read the graph, 0.30, 0.31, 3.0, 3.12. Okay, that's okay. I'm not going to argue about that difference like that. So the choice is yours. I think you should use the equations, but the graph just helps give you a feel. This is a road map. I have mixed flow. I start here, I go here, make a left turn, go on here, merge down here, now I'm turbulent flow. That's my road map. That helps me visualize what's going on in the problem. Okay, we took that problem a long way, so we're going to stop for today. We'll pick it up next time. We'll see you then on Wednesday. Don't go anywhere. We're going to give you the exams now.